Good day. Let me introduce myself. My name is Evgeny Buntov, and here I represent a scientific group, laboratory of physics of functional materials for carbon, micro and optoelectronics from the Institute of Physics and Technology, Ural University, Russia. We are working as a group for many years, but in 2017 a task came from our Moscow colleagues to study a new material, linear chain carbon, and we took this task both experimentally and theoretically, and today I would tell you about our modeling efforts to model the process of synthesis of linear chain carbon.
Сейчас, секундочку. Сейчас должна заработать.
Okay. First, I'm gonna give you some introduction about what is linear chain carbon. Next, we will talk about LCC structure and synthesis process. Of course, it's a plasma synthesis. Next, I will give a short overview of simulation methods and our modeling methods. Carbon materials are among the most extensively studied in the world now, partly due to many carbon outcrops out there, which is the reason of this is three main hybridization, sp1, sp2 and sp3, which give basic structures of diamond graphite, carbene and many derivatives. Carbene is a monoatomic chain of carbon atoms. Our research focuses on carbene-related structures, and objects under study currently the composite films containing linear chain carbon on copper, silicon and other substrates. Carbene or linear chain carbon has many distinctive properties. First of all, it has very anisotropic resistance, electrical resistance. Along the chain, it is 10 to 5 times lower than in perpendicular direction. Also, you may note low work function. That's why this material was used as a cathode for various electronic devices. Recently, in 2018, we discovered p magnetism in carbene. So to say, carbon doesn't appear a magnetic material, but if we introduce some kinks or bends in the chain structure, these structures induce p magnetic moment, which resides up to 400 K, and theoretically we proposed a method to further amplify this effect by doping with different dopants. And listed properties together with good biocompatibility ensure wide perspectives of LCC application. It's already applied in functional coatings, in medical implants, in energy storage, in medical applications, but mainly we focus on electronics and electronic properties of this material. What is the structure? What is the model structure of LCC? And the method of its synthesis. Firstly, I talk about the synthesis. Method is ion simulated deposition from carbon plasma. So we have, of course, a vacuum chamber and two crossed beams, main of which is a carbon plasma beam from graphite source. This plasma is obtained by electric arc discharge, and the parameters of operation are shown here. So it's pulsed process with up to 30 Hz frequency and 400 microseconds pulses in vacuum. But basically, this process itself, the carbon plasma deposition, gives us DLC films, so say diamond-like carbon. And in order to get an sp1 carbon, carbene or linear chain carbon, we should introduce a second beam, beam from gas ion source, argon beam, which makes favorable conditions for sp1 structure synthesis. And of course, we can add some gases here, basically hydrogen, nitrogen, to influence the properties of the film grown. What we get after synthesis is such non-monotonic dependence of electrical conductivity on the energy of argon ions. And this maximum and minimum correspond to breaking energies for different bonds, sp2, sp3 and sp1 hybridized. So if we choose properly choose the energy of argon ions and other parameters, we can get linear chains in our film. There is a photo of the experimental setup, which was located in very few cities in Russia, from Moscow to Cheboksary, Ekaterinburg, and even Dublin. And now, what we get if we set proper parameters is there is a 2D order crystal of chains. So this is a normal plane view and side view. And normal plane view we can easily confirm by electron microscopy, by AFM, or by electron diffraction. But this structure, this side view structure, comprising linear section of n atoms, then king, n atoms, and again a king. This is a model structure. It's more difficult to view by the standard characterization method. So what we use as characterization is XPS. This carbon 1s line can be decomposed into three components corresponding to different hybridization. By synthesis regimes, we can get more or less of sp1 content here, and we used also extensively Raman spectroscopy, which has some specific bands like bond length alternation along the chain, also indicating the presence of carbon chains. But still, even if we don't know the cross-section of sp1 hybridized atoms for X-ray photoelectron spectroscopy, still it's quite a low content in our conditions. And to get better results, we should understand both theoretically and practically the regimes and their influence on the film quality. So we started a project. We started a project of computer simulation of this synthesis procedure. First of all, I found this wonderful source, wonderful article, which provides a review of modeling methods for plasma synthesis processes. Here we can see different processes modeled by different techniques. First of all, ion stopping. For ion stopping and ion implantation, of course, people tried many different levels of theory. Next, ion and electron stick in absorption at the surface, cluster layer growth, surface reactions. So mainly in our investigations we should touch this sector, in which the most popular methods are molecular dynamics, quantum Boltzmann equations, and Monte Carlo methods. The problem stated here that there are two approaches from different sides. First of all, people study plasma properties. In this case, they use mostly fluid dynamics, and the solid border, the substrate, is described only by basically 4 numbers like sticking coefficients and diffusion coefficients, other parameters. So no atomistic treatment of the surface of the solid body is applied. And the next type of consideration is comes from social science and condensed matter physics, in which we have a slab of atoms, model of surface, and a single line falling to the surface. Both views are simplified, and to describe the whole process, the interaction of low temperature plasma with real atomistic surface, we need an integrated model which takes into account both plasma and surface on the atomic level. So in different length scales, we have different techniques, and here near the surface, this set of techniques is used. Basically, molecular dynamics, Monte Carlo, quantum Boltzmann equation, even Born-Oppenheimer molecular dynamics, time-dependent DFT, and non-equilibrium Gaussian functions. Some parameters are given from both sides. From bulk solid, we can perform DFT calculations and for example, develop specific force fields for for classical molecular dynamics. And from fluid simulations, we also can get the parameters of plasma, but at the core of the real synthesis processes, these methods are applied. Of course, they take not only different physical quality of description, but also different. They take different time to calculate the processes. So if you use time-dependent DFT, for example, we can go only up to 10 minus 30 seconds, 13 seconds, and not too much in length scale. And opposite for fluid simulations of plasma. We can go up to 1 second and up to thousands of micrometers or millimeters here. In the middle, there is a actively researched area of molecular dynamics, which could be extended by acceleration, by parallel calculations, by different techniques of acceleration of molecular dynamics. So we decided basically to start with this method and then extend it with appearing new techniques of acceleration. First of all, it was our first paper in this direction. We tested a very small thing, different molecules. You can find the chemistry names here, like butene, butatriene, tetramethylbutan. They differ by different order of central bonds. So single bond, double bond, and triple bond. And exactly the same conditions were applied for classical molecular dynamics with reactive force field, to Carr-Marinello molecular dynamics with quantum espresso, and to Ehrenfest dynamics with GPAV. You can see that this is the cost of step of this molecular dynamic simulation. If we go from simple to complex methods, we go from 0.05 to 4,500 milliseconds. So it's many orders of magnitude difference in time, and of course, the Ehrenfest dynamics gave best results as compared to experimental and high-level theory literature data, but it is prohibitively costly to apply to our full-scale simulations. Next, we found successful application of classical molecular dynamics for very similar processes of growing CVD, growing DLC films, and authors like Nates and others, they used two set of clusters and ions falling to the substrate with different fluxes, and they receive two different structures based on the composition of plasma flux falling to the substrate. All this was done with simple molecular dynamics, and we tried to repeat this stage. We took a realistic silicon substrate from this publication. We took the well-known 7x7 model of silicon surface. Next, in the depth, for molecular dynamics, we added a thermostatic layer, which ensures 300 K temperature during the synthesis processes. Also, there are free layers, free to receive these fallen clusters, fallen argon atoms, and so on, and some fixed layers modeling the 3D crystalline silicon structure. Then we've done a lot of simulations. Here, somewhere in Russian, we can see that both ion energy and angle of incidence were changed. many hundreds of simulations were performed, and they gave different quality. We summarized here an example. We drawn here an example of sticking of these molecules to the surface. So we were able to derive sticking coefficient for different species. Of course, some species have maximum coefficient, and some saturated species have minimum. To automatically analyze many results obtained, we proposed the quality criterion, which comprises four different criteria: total carbon atoms number on substrate, the number of sp1 carbon atoms, ratio of hydrogen to carbon, and number of chains in the results. So depending on energy, ion energy, and incidence angle, we are able to construct such a 2D map to select. There is a normalized value of C total to select the best regimes. So that was a test of classical dynamics modeling. Now we are going further. Now the test calculations are performed with hybrid QM-MM modeling process. So what is it? Part of the system should be described by classical molecular dynamics, and part of the system with DFT-based techniques. This method is very popular in case of biomolecules, which that have huge size, huge number of atoms. But here we also were able to use the software programs, LAMPS and GPAF, and connect them by atomic simulation environment based on Python to perform hybrid QM-MM calculations. So from this big picture, which is described by molecular dynamics, we can select small systems to be described by quantum laws and quantum dynamics. But the results are promising, but not yet ready to be presented here. And the next step would be to describe some charging processes between the ions of the plasma and the surface by even more sophisticated techniques such as TD-DFT and RFS dynamics. This is for the future. So, a challenge of LCC synthesis is to create an integrated model. Presently, none exist, so we are solving an open problem, but step by step we try to solve it. In our case of linear chain carbon, test simulations first were performed by molecular dynamics with reactive force field and argon ions bombardment. A criterion of film quality was developed. For plasma composition, we were able to determine the best regime, but of course it's not very real because of a low level of theory. We would like to improve this calculation on hybrid level. So hybrid calculations are now under test to describe the sticking processes with DFT accuracy. accuracy, and even further we can use TD-DFT and RNFest dynamics to include charging effects. So there is our team, and thank you for attention. I can answer your questions.
So I have one question. As I understand currently, well, you use very precision equipment, ion source, to treat your surface. What is the type of ion source?
Ion source is the plasma is obtained by is obtained by arc discharge from graphite cylinder here.
And the argon ion source, what is the...
Argon is actually it is a radical source of gas source of argon. So when it is used, of course, the level of vacuum here is worse. But by combining these conditions from carbon beam and argon beam, we can create needed regimes.
And it is real condition or condition which you use in your calculation?
This is a real condition. So we have at our institute we have a setup which I shown here, one like this, and we are experimenting. But still, for now, we have some know-how knowledge or artisanal knowledge, and don't have a good theoretical basis for that. So we try to develop one to get better appearance quality.
Okay, thank you. Any questions?